All right, today we're looking at the comparison tests. We're going to start with the direct comparison test. This says if you have a sequence A and sequence B, where B is bigger than A for all n values, so each term of B is bigger than each corresponding term of A, then direct comparison test says that if the sum of B converges, then the sum of A converges. So B is the bigger one. So if the sum of the bigger one converges, then the sum of the one that's smaller than it has to also converge, which makes sense. For 2, we say if the sum of A diverges, then the sum of B diverges. So if the smaller one is diverging, that means that the bigger one has to also diverge. The big thing with direct comparison test is picking what you're going to compare to. All right, so let's ignore the second one. We're just going to look at 1 for now. All right, we have 1 over 3 to the n plus 4. Now, when we pick something to compare to, we want to pick something that looks similar to it, but we already know the convergence or divergence for. So for this one, I'm going to compare to the sum from n equals 0 to infinity of 1 over 3 to the n. Now this we know the convergence of. This is a geometric series. Absolute value of r is equal to 1/3, which is less than 1. We know that this converges. And so if we look at the test says that if the smaller one or the bigger one converges, then the smaller one also converges. So we know this one converges. So if 1 over 3 to the n is bigger than 1 over 3 to the n plus 4, is bigger than 1 over 3 to the n plus 4, since the bigger one converges, the smaller one would also have to converge. So let's check. We have 3 to the n plus 4 is greater than 3 to the n. I just cross multiplied there. Then I'll subtract 3 to the n. We get 4 is greater than 0. That is a true statement that will not change no matter what n you plug in. So that means it is bigger. So let's create our statement. Therefore, since the sum from n equals 0 to infinity of 1 over 3 to the n converges by geometric series, then the series, let's say and since 1 over 3 to the n is greater than 1 over 3 to the n plus 4, then the series converges by direct comparison test. There we go. All right. So that's our statement. So all of these for direct comparison are just picking something that's kind of close to it. So if you want a couple you can try on your own. You have this one right here, which you can compare to the sum from n equals, let's say 5 to infinity just to match, of 1 over n to the 1/3. There's a p series that we know diverges. So it's going to be a very similar process. But this time, since it's diverging, you're going to show that 1 over n to the 1/3 is less than 1 over the cube root of n minus 4. All right, so I'll let y'all try that one. The next one we're going to look at is the limit comparison test. Now, this one is more broadly applicable because you don't have to know which one's bigger or smaller. This one says that if you have two sequences, and if the limit when dividing those two sequences is equal to a positive finite number, then they either both converge or both diverge. So as long as you know what one of them does, then if you divide them and do the limit, you know what both of them do. Now, I'm going to go ahead and jump straight to this one right here. Okay, let's jump straight to this one right here. So if we were to figure out what we need to compare to with the limit comparison test, what we're going to look at is we're going to look at the biggest degree of the top and bottom, or the biggest property of n. Let's put it that way, because sometimes you'll have factorials, sometimes you'll have exponentials, and so you want just the biggest property of n on top and bottom. And that's what we're going to compare to. So we're going to do n equals, and we really should change this to 1 because it won't work for us if we don't do it. N equals 1 to infinity of n to the 1 over n cubed. And that'll simplify down for us to a nice 1 over n squared. All right, and we know what this series does. This is a p series. P is equal to 2, which is bigger than 1, so it converges. Okay, so we know what this one does. So now what we're going to check is the limit when we divide them, so 100 plus 7n over n cubed plus 2 divided by 1 over n squared, is that a positive finite number? Well, let's go ahead and do it. So when we divide, that's the same as multiplying by the reciprocal. So this is going to be times n squared over 1. So this limit as n goes to infinity of 100 n squared plus 7n cubed over n cubed plus 2. All right, this is just leading coefficient for this limit, so this equals 7. That's a positive finite number, so we can say, since the sum from n equals 1 to infinity of 1 over n squared converges by p series, and since the limit as n goes to infinity of 100 plus 7n over n cubed plus 2 divided by 1 over n squared equals 7, then the series converges by limit comparison test. And there we go. All right, so these are the comparison tests. Direct comparison test, you're showing that one is bigger than or smaller than the other. Limit comparison test, you're finding the limit when dividing them. All right, let me know if you have any questions. You'll have a great day.